All right, so the right here is in your notes. It's the very end of this is about alkenes, and this is some properties and uses. So what you'll notice is most alkenes have a low mass, and when you have a low mass, it typically makes it easier for you to be one of the states of matter that have more energy. So most alkenes tend to be gases. They are nonpolar, and what that means is that they, if you remember, they share electrons equally. They're used in a lot of plastics, alcohols, and then one thing I think is pretty cool is we're pretty lucky that we can get all sorts of fruits and vegetables from all over the world and at really any time of the year. And what they actually do is they'll pick them when they're not in season. They'll pick them when they're not ripe, and they'll ship them almost frozen. And then what they do is they actually expose them to ethene, and then that chemically ripens them. So a lot of people say like, oh, if I go and buy fresh strawberries from like a farm stand, they taste better. And it's typically because they're naturally ripened as opposed to a chemical ripening. So just some cool things about alkenes. There is some sections in your book that you should read on them, but that's just some of the things you use alkenes for. The last type is of hydrocarbons we're going to talk about are alkynes, and again that ending, the suffix here, alkynes, is indicating something, and an alkyne indicates that there is at least one triple bond somewhere in there. And again, it's just using that suffix to indicate that. If it is a normal alkyne, you have a magical formula that'll tell you how many hydrogens and carbons there are. They follow the exact same rules as the alkenes. The only difference is that it ends in Y and E. So like, for example, if we're looking at number 2 down here, we have 3 carbons. We definitely have a triple bond. This would be our number 1 carbon, our number 2, and our number 3. Same thing, triple bond's the most important, so that's where we number that from. And if we count this out, this would be meth-prop. This would be a 1-propyne. And again, you're just giving that number 1 because the triple bond is between the 1 and the 2, and the lower number wins. So that's where that comes from. If you have something hanging off, like if we look at number 4, here we have 4 carbons in a line, so that's our longest chain, and then we have this methyl group. Now typically, if this was not an alkyne, if this was just an alkane, we would actually number it from this end because of the methyl group hanging off. But because this is a triple bond, and this is the thing that's more important, we actually number it from this end. So this is our number 1 carbon, this is our number 2, and so on and so forth. And when we number this guy, what we end up having is we have a 3-methyl, 1-meth-prop-bute, butene. So we didn't do very many alkynes because they're so exactly the same as the alkenes. You just have to remember the difference in the triple and the double bonds. Just a couple things. Triple bonds are actually kind of unusual because all the atoms are in a straight line. They're actually pretty unstable, and this is a lot of electrons to have in one place. So a lot of times these guys will actually be very, not explosive, but chemically reactive. And again, that triple bond is what's going to be the most important when you're dealing with these. Just a little loose ends to tie up here. We said that we've been dealing with when carbon only bonds to carbon and hydrogen. We did say that it can bond to other things though, and organic halides are an example of that. So organic halides are when you have an organic compound and then you have it attached to a halogen. So if you remember, the halogens are group 17 on the periodic table. So you could have fluorine attached, which we call fluoro. You could have chlorine attached, which we call chloro. Bromine, which is bromo, or good old, my favorite, iodo. The only one you really have to watch out for is the chlorines because they kind of look kind of blended with the carbons. But they do follow the exact same thing, and these guys, the fluorine, the chlorine, the bromine, and the iodine, you just treat them, or iodo, you treat them like a methyl group or an ethyl group. So like, for example, if we look at this first one, you find your longest chain, single bonds and everything, and you say, oh, there is a chlorine hanging off here, but it makes it different. So when you do your naming, you still do it. Numbering still applies. Chlorine, you want to have the lowest number. So this would be my number 1 carbon. This would be my number 2. This would be my number 3. And then everything else follows the same. Really, the only thing that's different is that I'm not going to call this a methyl group or a propyl group or anything. This is going to be a chloro group. So when I name it, I call it a 1-chloro. And then I have 3 carbons, single bonds. So it's meth-s-prop. And single bonds ends in A-N-E. So this is 1-chloropropane. And if you look at number 2, same thing, find your longest chain, find anything that's hanging off of it. So we have a chloro group and a methyl group. And again, more things are hanging off on the right side. So this is our number 1 carbon, and again, so on and so forth. Now, don't forget, you have to go alphabetical. So alphabetically, chloro comes before methyl. So when we do our final name, we have a 1-chloro, 2-methyl, propane. And these 2 here, we'll actually do 4 before 3. They're just kind of putting extra things together here. So where you're kind of starting to merge ideas together, which is important because you want to be able to take something that you know and apply it in a new situation. So if we're looking at this guy, if we're going to do number 4 first, our longest thing here is this box, or it's a cyclo. So if we think of like our longest chain, what we're going to call him is we have 4 things in a circle. So it's going to be a cyclobutane. And again, but means 4, ane means single bonds, and the cyclo means that it's in a circle. And then we also have a chloro and a methyl. Now we have to number it, but again, it's a circle, so we can start numbering it anywhere. So I'm just going to make that my number 1 carbon because it makes my life a lot easier. And then the last thing we have to do is remember, because there's different types, we have to go alphabetically. So chloro is going to become before a methyl group. So what we get is we're going to get a 1-chloro, 1-methyl, cyclobutane. And again, it's all one word all put together. And number 3 is kind of tricky. So, I mean, you're welcome to try it on your own, but we're going to go through it just because it can be a little weird with this. So we have a couple of things going on. Obviously, our biggest thing here is we have this ring that's made up of 5 carbons. And then we also have some things hanging off here. We have a chloro, we have an iodo, and the other thing we have to worry about is we have a double bond here. So you just kind of have to keep that in mind when we're doing this. So if we're looking at our longest chain is 5 carbons in a ring, and there is a double bond, so it will be a cyclopentene. And we're going to have to number it, but we're going to choose our numbering carefully. So we have to choose how we number this. We want our double bond is the most important. It has to be somewhere. So either this carbon is going to be our number 1 or this carbons are going to be our number 1. Now usually when you do like double bonds and triple bonds, they're kind of like between the 1 and the 2 or the 2 and the 3. But with a ring, they don't have to be. They can be kind of like all over the place. So what the best way for this to number is if this guy right here is our number 1, because that means our double bond is on the 1 carbon, and that's the most important. And then what we can do is we can go counterclockwise around it to give the other guys the lowest possible. So this is a 2, this is a 3, a 4, and a 5. So it's unusual that the double bonds between a 1 and a 5, but in rings that can happen, and that typically happens because it gives other things lower numbers. So when we put it all together, alphabetically still, we worry about it, and chloro is before iodo. So we're going to say 3-chloro, 2-iodo, and then we're going to say we have to have our number, and again for the double bond it's between the 1 and the 5, so we're going to pick 1, and it's cyclopentene. So these are things, you're not going to have tons of these on your test, but these are the kind of things where you have to be able to put ideas together. It's not just like one double bond. It's not just one chlorine. How do we apply them together? And there's just one thing that's really important about these halogens. What you've probably heard of before is you've heard of CFCs, or you've heard of what bad things they can do to the ozone hole, and these are some of the most widely used chemicals, and they're organic carbons, and they have chlorines and fluorines attached. And the problem is that they're very good at sequestering ozone oxygen. So they were used extensively to make plastic foams. They were the best refrigerants we have. Freon is a CFC, and the concern is that when you have ozone is naturally unstable. So this is what ozone looks like. It's 3 oxygens. You have one side with a double bond and one side with a single bond. Ozone is naturally not a stable compound. It does break apart. And what they were finding is that the CFCs were being able to bond to these oxygen molecules, and it was preventing them from reforming ozone. Because what would happen is the ozone molecule would be around for a while, it would fall apart, and then eventually some of the oxygens would bump into other oxygens and make a new ozone. And to put it very simply, the CFCs were kind of getting in the way, and they were preventing the ozone from reforming. So what they've done is a lot of countries have banned these. Like, we don't use Freon anymore in our country. A lot of the developing countries still use them because it's they're harder to manufacture. But if you need refrigerants, you need refrigerants. So just one thing where we weren't trying to be bad to the environment. We weren't trying to kill sequester ozone. But when you use chemicals and when you manufacture chemicals, there are consequences.